Swayam Prabha. Digital India. Educated India.
So, in the last class we discussed two control schemes. One is P only controller and another one is PI controller. So, first we discussed the P only controller followed by the PI controller. We made few conclusions on this P only controller. Like first conclusion on P only controller is it speeds up the response of the closed loop process. P only controller speeds up the response of the closed loop process. It speeds up the response. Fine. And with the increase of Kc value, the controller becomes more sensitive to error signal. With the increase of Kc value, the controller becomes more sensitive to error signal. With the increase of Kc value, the controller becomes more sensitive to error signal. Fine. The P only controller does not eliminate offset. Third conclusion, the P only controller or proportional action you can say does not eliminate offset. P only controller does not eliminate offset. Fine. The PI controller consists of proportional action and integral action. PI controller includes two control actions, those are proportional action and integral action. So, if we consider the integral action, then we can say that integral action eliminates the offset. This integral action eliminates the offset, and that is why this integral term is included with P only controller to make PI controller. Fine. Now, today we will study the elimination of offset by PI controller. How the PI controller eliminates the offset, that we want to observe. Fine. Now, we will discuss the elimination of offset. What is offset? As mentioned earlier, offset is described as a steady state deviation of the controlled variable from set point. Offset is the steady state deviation. It is mentioned earlier that the offset is defined as a steady state deviation of the controlled variable from set point. Fine. Offset is defined as the steady state deviation of the controlled variable from set point. Now, we will consider one example. This is a tank heater. Fi is the inlet steam flow rate and Ti is the temperature of the inlet stream. Outlet is coming out with flow rate F and temperature T. Height of liquid in the tank is H and temperature is T. A heating medium, steam is introduced through this coil with a flow rate of F suffix St. Fine. Now, we are assuming here that the inlet and outlet flow rates are identical. And both are constants. We are assuming the inlet flow rate and outlet flow rate as constants and they are both are identical. So, what it indicates? There is no variation of height. So, height is constant. If both the inlet and outlet flow rates are equal and constant, then there is no variation of liquid height. So, for this process, what is the controlled variable? Which one is the controlled variable? Temperature. Manipulated variable is steam flow rate, and which one is load variable? Fi is constant, that is why load variable is Ti. Fine. Fi is constant. So, Ti is the only load variable. Fine. Now, we are considering the steady state conditions as Ti equals 25 degree Celsius, T 60 degree Celsius, fine, and at steady state the steam valve is 50% open. At steady state the steam valve is 50% open, at steady state the temperature of inlet steam is 25 degrees Celsius, the temperature of liquid in the tank is 60 degrees Celsius and the valve is 50% open. These are steady state conditions. Next, we will consider a step change in load variable. Another thing I want to mention here that this valve is air to open. This valve is air to open. It means if the input pressure is increased, the valve opening increases. With the increase of inlet pressure, the valve opening increases. Next, we will consider the step change in load variable. Step change in load variable. As mentioned, Ti is the load variable and at steady state Ti is 25 degrees Celsius. Now, we will introduce a step change in Ti, that is represented in this plot. This is time, this is Ti. Initially Ti is 25 degrees Celsius. Now, it is changed to suppose 20 degrees Celsius at time t equals 0. We are introducing a step change in Ti, that is from 25 degrees Celsius to 20 degrees Celsius. Fine. Now, we will note down few points. The larger the value of Kc, the smaller the offset. The larger the value of Kc, the larger the value of Kc, the smaller the offset. Fine. If we introduce this step change, I mean from 25 to 20 degrees Celsius, then the process responds under P only controller like this. This is T, this is temperature. What is the steady state value of temperature? 60 degrees Celsius. Fine. Now, if we introduce a step change at say time t equals 0, the closed loop process responds like this. Fine. This is at a particular Kc value. So, we can write the title as process response under P only controller, under P only controller. Fine. A P only controller is employed around that tank heater. Now, we introduce a step change in Ti, then the process, I mean the closed loop process responds in this manner. If we consider another Kc value, then the process responds like this. Fine. If we consider a different proportional gain value, then it responds like this. Now, here Kc1 is greater than Kc2. This is the observation. If we introduce a step change in Ti, the tank heater system under P only controller responds in this way. That is why we concluded here that the larger the value of Kc, the smaller the offset. Fine. This is the offset for the case of Kc1. This is offset. And for Kc2, this is the offset. Now, if this is the conclusion, I mean the larger the value of Kc, the smaller the offset, then why not set a maximum gain? Immediately one question arises, why not set a maximum gain? For most of the processes there is a maximum value of Kc, there is a limit of Kc. For most of the chemical processes there is a maximum value of Kc that we can represent by Kc max. If we consider Kc greater than Kc max, then the process goes unstable. For most of the processes there is a maximum value of Kc represented by Kc max. If we consider Kc greater than Kc max, there is a high probability of instability problem. Fine. And this Kc max is called ultimate Kc. This Kc max is called ultimate gain represented by Kcu. Fine. So, we cannot consider arbitrarily large Kc value to reduce the offset, there is certain limitation. Now, with the decrease of tau I, what happens? In this case, I mean we have considered a decrease of tau I. If we decrease tau I, the temperature of the liquid in the tank decreases. Agree? If Ti is decreased, the temperature of the liquid in the tank also decreases. Fine. Then what is required to do for the controller to keep the temperature at 60 degrees Celsius? The controller needs to increase the steam flow rate. Fine. Now, we have considered at steady state the valve is 50% open, but if Ti is decreased to 20 degrees Celsius, then suppose the controller needs to open the valve 60%. At steady state, we have considered 50% opening of the steam valve. If Ti changes from 25 to 20 degrees Celsius, in that case suppose it is required to open, it is required to 60% open of the valve to maintain temperature at 60 degree Celsius. Fine. Now, our manipulated variable is Fst. Our manipulated variable is Fst. If we consider P only controller, then we can write Fst equals Fst S plus Kc error t for the case of P only controller. Our manipulated variable is f s t. So, if we consider P only controller, then we can write this equation f s t equals to f s t s plus k c epsilon t. What is f s t s? Steady state value of f s t. If we represent f s t in terms of percentage opening, then f s t s is nothing but 50%, because that is the steady state value of f s t. Fine. And how much the second term will be? How much will be k c epsilon t? Remaining 10%. Agree or not? F s t s is the steady state value of f s t. We have considered 50% opening at steady state. So, f s t s we can write as 50%, and the rest k c epsilon t will be remaining 10%. Fine. So, what it indicates? I mean, k c epsilon t equals 10%. So, how much epsilon t? At least epsilon t is not is equals to 0. If k c epsilon t equals 10%, then epsilon t is not is equal to 0, because the controller gain is non-zero. Since k c is non-zero, so epsilon t not is equals to 0. It indicates there will be an offset, because error not is equal to 0. It indicates there is an offset under P only controller. Fine. Next, we will consider the PI controller. We will continue the same example and we will consider PI controller. PI controller. As long as the error is present, the PI controller keeps changing its output by integrating the error. If we see the controller equation, f s t equals f s t s plus proportional term k c epsilon t plus integral term, that means k c divided by tau I integration error dt. This is the PI controller equation. Fine. So, this is the integral term. As long as the error is present, the PI controller keeps changing its output by integrating the error. Okay. Now, if we consider f s t 60%, how much is f s t s? 50%. How much is this one? PI controller eliminates the offset. If that is the case, then error should be 0. So, k c epsilon t is 0, and this term is 10%. If we see the plot, we observe that the PI controller, the process under PI controller reaches at steady state value. I mean, the process under PI controller remains at steady state temperature, but for the case of P only controller there is an offset. So, this is the process response under P controller and this is the process response under PI controller. Fine. Now, you see, if we introduce a step change in Ti from 25 to 20 degrees Celsius, then there is a need to open the steam valve 60% open. There is a need to maintain 60% opening of steam valve. So, this is 60%, steady state value is 50%. If PI controller eliminates the offset, then definitely error should be 0, that means this is 0. So, remaining 10% is indicating the integral term. This remaining 10% is provided by the integral term. So, it is not 0, it is not 0, it remains constant, it remains constant at the last value. I mean, epsilon at a last time step is 0, but the sum of remaining errors, previous errors provides 10%. The last error, that is epsilon t, equal to 0, fine, and the sum of previous errors provide 10% opening. So, this indicates that the error, I mean the steady state error can be reduced to 0 under PI controller. So, we will discuss this with a more rigorous proof later. We will discuss this with a more rigorous proof later. Fine. Next topic is reset window. Reset window happens for PI controller. This happens for PI controller. Now, for PI controller, we know that as long as the error is present, the PI controller keeps changing its output by integrating the error. For PI controller, we know that as long as the error is present, the controller keeps changing its output by integrating the error. Fine. So, as long as the error is present, the PI controller keeps changing its output by integrating the error. When a sustained error occurs, the integral term becomes quite large and the controller output eventually saturates. When a sustained error occurs, the integral term becomes quite large and the controller output eventually saturates. When a sustained error occurs, the integral term becomes quite large and the controller output eventually saturates. Further build up of integral term is referred to as reset window. Further build up of integral term is referred to as reset window. So, as long as the error is present, the controller keeps on changing its output by integrating the error. When a sustained error occurs, the integral term becomes quite large and the controller output eventually saturates. Further build up of integral term is called reset window. Now, to reduce the reset window, there is a need to devise anti-reset window. To reduce the reset window, there is a need to devise anti-reset window. So, there are many ways to devise this. So, one we will discuss here, one we will mention here. Reset window is reduced by temporarily halting the integral action whenever the controller output saturates. Reset window is reduced by temporarily halting the integral control action whenever the controller output saturates. This is the one way to devise the anti-reset window. Fine. So, next we will discuss the third controller, that is PID controller, proportional integral derivative controller. Next we will discuss proportional integral derivative controller. In short, this is PID controller. Fine. The name suggests that the controller includes three actions: proportional action, integral action and derivative action. Now, if we consider manipulated variable, if we represent manipulated variable as C, then the PID controller can be written as Ct equals Cs plus Kc epsilon t plus Kc divided by tau I integration error dt plus Kc tau d d error dt. This is the proportional action, this is the integral action and this one is the derivative action. This is the proportional action, this is the integral action and this is the derivative action, and CS is the bias signal. I mean when error is 0, the controller output is CS. So, we can rearrange this equation as C prime t equals Kc error t plus 1 divided by tau I integration of error dt plus tau d d error dt. Fine. We can rearrange the PID controller in this form. Now, we wish to derive the transfer function of the PID controller by taking Laplace transform. If we take Laplace transform and if we rearrange, then we get C bar prime s divided by epsilon bar s, which is GC and GC equals Kc 1 plus 1 divided by tau is plus tau ds. This is the transfer function of PID controller. Fine. This is the transfer function of PID controller. Now, you observe one thing, that if error is non-zero, what about the derivative action? If error is constant and non-zero, what about the derivative action? 0. There is no existence of derivative action, because derivative action is equal to Kc tau d d error dt. If error is constant, then the differentiation of that with respect to time becomes 0. So, this point we can note down as first point. Secondly, for a noisy response with almost 0 error, for a noisy response, I mean for noisy y, because epsilon is y set point minus y. So, noisy response means noisy y with almost 0 error. D term leads to large control action, although that is not needed. For noisy response with almost 0 error, D term leads to large action, derivative term leads to large control action. Although that is not required. So, we can say this is unnecessary. Fine. You can say this is a drawback, these two are drawbacks of PID controller. When error is constant, there is no action from derivative action, and when there is noisy error, the derivative action unnecessarily is large. So, these two are the drawbacks of PID controller. Next, we will discuss the control actions. One is direct action, another one is reverse action. we will discuss next direct and reverse actions. So, as the input signal to the controller increases, the output signal from the controller should increase for direct acting controller. You note down this point. As the input signal to the controller increases, as the input signal to the controller increases, the output signal from the controller must increase. The output signal from the controller must increase for direct acting controller. For direct acting controller. Fine. Similarly, we can say that as the input signal to the controller decreases, the output signal from the controller must decrease for direct acting controller. So, we can say that if the input signal increases, the output signal should increase for direct acting controller. In reverse, we can say that if the input signal to the controller decreases, the output signal from the controller should decrease. Therefore, for direct acting controller, these two terms are used, increase or decrease. To indicate the direct acting controller, these two terms are used. One is increase, another one is decrease. Fine. We will take one example to discuss this action, direct action. This is a liquid tank system. This is a liquid tank system. Our controlled variable is liquid height and manipulated variable is suppose F naught. Controlled variable is height and manipulated variable is F naught. So, to maintain the height we need to employ one level controller. I am not showing the sensor, comparator, etc. here. Directly we put here the block for level controller. Fine. Now, if height increases, suppose if height increases, what is required to do for the controller? The controller should increase F naught or decrease F naught? Controller should increase F naught. If height increases, the controller should increase F naught to maintain the height at its desired value. You see, the input signal to the controller, that is height, if increases, the controller is increasing the output signal F naught. So, this is direct acting controller. This level controller is direct acting controller. The input signal height if increases, the controller increases accordingly F naught. So, this is direct acting controller. Now, we will write the controller equation. Suppose this level controller is a P only controller. Accordingly, the controller equation is written as f naught equals f naught s plus Kc height set point minus height. Suppose this level controller is a P only controller. Accordingly, we can write the controller equation as f naught equals f naught s plus Kc error. Error means h set point minus h. Now, if height is greater than h set point, if height is greater than h set point, so what will be f naught? It will be greater than f naught s or less than f naught s? It should be greater than f naught s. Agree? If height is greater than h set point, then the controller required to maintain this condition, I mean f naught should be greater than f naught s. If height is greater than h set point, then what about this term? It is positive or negative? It is negative. Now, how it is possible to maintain f naught greater than f naught s? Kc, if Kc is negative. Fine. If height goes above set point value of h, then from this equation it is clear that the error becomes negative. Now, controller is required to maintain f naught greater than f naught s. That is only possible when Kc is negative. So, we need to remember that, we should remember that for direct acting controller, the controller gain is negative. This is the most important feature of direct acting controller. For direct acting controller, the controller gain should be negative. Fine. Next, we will discuss the reverse action. Reverse action. It is just reverse of direct action. So, definition is, as the input signal to the controller increases, the output signal from the controller should decrease for reverse acting controller. As the input signal to the controller increases, the output signal from the controller should decrease for reverse acting controller, or as the input signal to the controller decreases, the output signal from the controller should increase for reverse acting controller. Fine. If we continue the same example, what will be the manipulated variable for reverse acting controller? Height is the controlled variable. So, Fi should be the manipulated variable for reverse acting case. You see, if we increase the height, what is required to do for the controller? The controller should decrease Fi to maintain height at its desired value. If height increases, the controller should decrease Fi to maintain the liquid height at its desired value. That means it is reverse acting. Fine. Now, we will write similarly the controller equation. Fi equals Fis plus Kc h set point minus h. Now, if height is greater than h set point, Fi should be less than Fis. If height is greater than h set point, the controller should maintain this condition, that is Fi less than Fis. Now, if height is greater than h set point, then the error becomes negative. Now, how the controller can maintain Fi less than Fis? If Kc is positive, agree? If height is greater than h set point, then the error becomes negative. Now, to maintain Fi less than Fis, Kc should be positive. So, similarly, I mean like direct acting controller, unlike direct acting controller, the controller gain should be positive for reverse acting controller. Next, we will discuss another controller, that is on off controller. On off controller. This is the simple, inexpensive feedback controller. On off controller is the simple, inexpensive feedback controller. Fine. Like an ideal on off controller, we can represent as Ct equals Cmax. If error is greater than or equal to 0, Ct is the controller output. So, when error is greater than 0, Ct provides maximum value, Cmax. That means, if you consider a control valve, C provides 100% opening. So, if we consider a control valve as a final control element, then Cmax indicates full opening of the valve. Similarly, this Ct becomes C min if error less than 0. The controller output becomes minimum value of C when error less than 0. If you consider a control valve as a final control element, this indicates full closing, I mean this indicates fully closed. There is no intermediate control action, either maximum value or minimum value. That is why the name on off. Fine. Now, we will consider few cases, like for digital computer implementation. For digital computer implementation, Cmax indicates 100% and Cmin indicates 0%. If we consider a current based electronic controller, this Cmax indicates 20 milliampere and Cmin equals 4 milliampere. For current based electronic controller, maximum value is 20 milliampere and minimum value is 4 ampere. Similarly, if we consider pneumatic controller, controller. Maximum value is 15 psig and minimum value is 3 psig. If we consider pneumatic controller, C max is 15 psig gauge pressure and minimum is 3 psig. What is the use of this on off controller? On off controller is used in home heating systems. On off controller is used in home heating systems. On off controller is used in domestic refrigerator. This is used in domestic refrigerator. On off controller is also used in laboratory furnaces. Fine. Now another thing we can say that if Kc value is very large for P only controller, then the controller behaves like on off controller. If Kc value is very large for P only controller, the controller behaves like on off controller. Definitely the proportional controllers are more efficient than on off controller. The proportional controllers like P, Pi, PID are more efficient than on off controller. Thank you.